Hello, welcome back to this class. This class is about Transformer Decoder, and in this class, actually, we're going through all parts of Transformer Decoder. So we are going to explain bit by bit or process by process of this uh, uh, Transformer Decoder. Now, here is the encoder, actually. That's the encoder. This part is the encoder. And we're going to talk about each part of this encoder, each box of this encoder. So here we talk about the whole process of this encoder. Now, uh, uh, transformer encoder, it has so many parts. One of the parts is input embedding, which converts words into numerical vectors. And what I mean by words is these are the tokens, okay? Positional encoding adds information about position or the order of each token. Self-attention allows each token to look at each other, sorry, and learn relationship. Multi-head attention uh, different learns different types of relationship from multiple attention perspective. And masking means the model prevents from seeing future tokens during generation. Add residual connection. This one, it will preserve original information and adds new learned information. Layer normalization. This one speeds up the training. It normalizes it. And feed forward network. This one further processes and transforms each token representation. Drop out, this is good for overfitting. It skips some connections. Linear layer converts the final representation into scores for possible output tokens. And Softmax converts tokens into possibilities of the next token. So it tells you what is the possibility of the next token to be predicted. Now, decoder input is the input which is the target sentence shifted right. Usually we call it teacher forcing for training. So we feed the start token and previous token. For example, if we have a target Arabic translation of I like Rojava, okay, we had a sentence in English, I like Rojava. And the target Arabic translation of this sentence is kind of might be أنا أحب Rojava. So for calculation, we represent tokens as embeddings. So target input sequence is the translated sentence for the word that we need to be translated. So for example, I like Rojava, I need to translate it. It'll be start token and ahab. We call it decoder input or input decoder. Now, we assume we embed them into vector of size four features, and three tokens that start, that's Ana, and the last one is ahab. So now you have three rows, each one of them is a token. The first one is star, the second one is Ana, and ahab. Now, we add positional encoding for the decoder and details of positional encoding. It was done in the encoder, and you can go back to the encoder positional encoding, and it has the details about how this process is done. Now, I like Rojava into Arabic. That is the decoder input shifted right. Now, convert token into embeddings. We have D model is four features, and for token S and I have, this is the Y matrix. So 3 by 4. Now we need to define positional encoding. Positional encoding adds sequence order information. We said that because there's no recurrence and there's no LSTM, long short-term memory, or previous models, so transformer will enter the sentence in parallel. So therefore, we need positional encoding. So positional encoding, assuming that this is the positional encoding the for the word, for the sentence S, Anna, Ahab. So this positional encoding PE plus Y will give us positional embedding. So element-wise, 0.01 plus 0.1, 0.02 plus 0.52, and so on and so forth. We added, we added we added here, sorry, we added positional embedding, and that's the output of positional encoding. So that's the output of positional encoding. This is the first part is done. That's the first part is done. Positional encoding is done. Now next we go to masked multi-head attention. Now we are in this one. Now so in the decoder self-attention with masking, well, each token can only attend to previous tokens, including itself. So for token S, the S can only attend to itself, and Anna can attend to itself and to previous token, which is start token. However, token Ahab, the last token, can attend to itself and to itself and to Anna and to start. And why is that? Because masking, ensures future tokens are not seen. Now, but here, because this is the last, ahab is the last word, the last token, so there is no need, there's nothing left in the future, so it can see it. So here, start can attend to itself, Anna can attend to itself and to start. Ahab can, but cannot, Anna cannot attend to Ahab. Ahab can attend to itself and to Anna and to start. So something like that. Now, we need to provide or initialize some of the weight matrices for WQ, WK, and WV. V is the values and K is keys and Q is the query. So assume for simplification that we have this matrix 4 by 2, 4 by 2. So that's the weight matrix. We're trying to find Q1, query 1. Query 1, that's the output. So this output, this multiplied by, this row multiplied by this column and this column. Likewise, this row multiplied by this column and this column. So, and likewise, third row, which is ahab, multiplied by this column and this column. So just a simple row multiplied by the columns. Now, when this is the first row multiplied by the column, the first row, first row, the first row, That first row multiplied by the column, and the result is this one, 0.42, 0.75. And the second row, we multiplied by the second column, and we get the second column. And likewise, third row multiplied by the first column and second column, we will get that value. So that's the Q was found and K was found. We're assuming that, because we assume that we have the same weight matrix, so all of them, they will have the same value. This is only for learning. So Q, we said that Q comes from the first row multiplied by this column and that column. Second row, this one, multiplied by this column and this column, and third row multiplied by this column and this column. Now these are the results for Q, K, and V. Now next, apply mask. What we are going to do, mask feature tokens. For example, start here cannot see Anna and cannot see Ahab, but Anna here, Anna, this one is 0, can see start. And the last one, Ahab, this one Ahab, can see Anna and can see start. Why? Because the last token, there's no future token after it. So that's the idea. So any token that we cannot see, we put infinity, minus infinity for this allowed position. Okay. Now, here we have the Q, K, V, the softmax formula plus mass multiplied by V. Now, dk, our D model is 4. So 4 divided by 2, dk is 2. Now, square root of 2, we will have 0.707. Okay, square root of k, we will have 0.707. Now, here we have to do this operation, Q multiplied by K transfer. So this is the Q, and K transfer is the same Q as we mentioned, because they have the same weight matrix for all of them. So we should have the same K, but the transfer, it will be 2 rows and columns. Okay, so this row multiplied by 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 this, and this row multiplied by this row multiplied by this row multiplied by this, and we will get QKT. Then we divide it by dk square, then that's scaled, and then plus mask, we multiply it by value, then we get the attention. Here is the done for token 1, and here is done for token 2, and he's done for token 3, and that's the result of the dk QKT. That's the result of QKT. Now, scale each value of this one divided by square root of dk, divide by square root of dk, each value. So we will have this result. So we will have this one, that's the scaled value. Now, the scaled value, here we apply masking, and when we apply masking, so that we prevent looking at the future. So this is S, this is Anna, this is Ahab. First row, start, second row, Anna, then Ahab. So the first row, start, cannot attend Anna. So cannot attend Ana. So this one is minus infinity. Again, the 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 first row start cannot attend ahab. So it's infinity. While the second row here, this position, second row, second cell, column, second cell. This one, 0. This one is Ana, can attend itself and can attend start. And the last row, this is Ahab, can attend itself and can attend Ana, can attend start. That's how it works, because there's no future token here. That's why a token can see itself, can see also previous tokens. Now, adding element-wise, for example, 0.52, we just try to get, okay, just get, now, add, sorry, okay, add 0.5 to 0, 0.52, add 1.101 to infinity, it will be infinity. Add 0.765 to infinity, minus infinity, we get minus infinity. Add 1.101 to 0, you'll get 1.10 to 0. So basically, what I did, very simple, this plus this element-wise. So this adding to this adding to this adding to this, and so on and so forth. This adding to this. So we'll get this result. So that's our result. Now, what does it say? What does it say? So add mask element-wise 0.2, 0.52, infinity, minus infinity, minus infinity. So that means the start token cannot see Ana and cannot see Ahab. And Ahab cannot see Ana. Ana cannot see Ahab. And Ana can see itself, 2.59, and can see start. And Ahab can see itself, can see Ana, can see start. That's the idea. Now we do apply softmax to it. Just applying softmax e to the exponential each feature over the sum of the feature in each row. Exponential is done, softmax is done row-wise. So we'll take every row. For the first token, we will get exponential of this one, exponential of this one, exponential of this one, and then adding them up. And then this one divided by the sum. So 0.522 divided by 0.522, that's 1. And exponential to the power of minus infinity 0, and exponential to the power of minus infinity 0. So we have 1, 0, 2. Now, the softmax for each token, the summation of all features should equal 1. So 1 plus 0 plus 0, that's 1. Likewise, for the softmax for token 2, we would have this result. So 0.195, 0.8500 plus 0, they should all equals 1. And this one also should equals 1. This also should equals 1. Now, we multiply by V so that we can get the result, and the result multiplying the results of the Q, K transfer scaled over dk square root subject to softmax multiplied by V, we will get, so Q, K, T over square root of dk softmax multiplied by v, you should get this result. So that's the result that we will get. That is the decoder's self-attention output. Decoder self-attention output. Decoder self-attention output. Here, if we just go back, 100, what does it mean, this one? Well, it means that token S, one means token S start attends to itself almost and does not attend to anybody, to any future. And here, what does it mean? It means token ANA 0.85, which is the highest, attends to itself and attends to previous, but does not see future. And here, token AHEB attends mostly to itself, 0.48, the highest, but also attends to AHEB, attends to AHEB to itself, and attends to ANA, and attends to start. So AHEB here, that's third token I'm talking about, attends to itself by 0.3086 and attends to ANA weight token by 0.481 and attends to start by 0.213. So that's the translation for it. Now, so far we have done with this one and we have done this one. Now we do add and normalize. Let's do add and normalize. So this one we do add and normalize. So adding this one to the original output here. We have this output. That's the output. That's white position. Here, that goes here. We add it to the output from multi-head. So the output from multi-head plus this one, that is adding residual. So from the multi-head, before multi-head is this one, and multi-head is this one. So we add them to each other. Now adding them to each other 4-dimension, it cannot be done because this is 4-dimension, but this one 2-dimension. So what we are going to do technically, we copy this one more time here. Okay, so we copy it one more time, the same values. This is a copy of this one. Now, after that, we do the adding 0.11 plus 0.42, 0.52 plus 0.75, 0.31 plus 0.42, 0.23 plus 0.7, and so on and so forth for all other limits. And now that's we should have the results for it. Now, once done this one, we do what? We do layer normalization. Layer normalization means that we will have this token, that's the result. We sum up each features and divide it by 4. This is the layer. We sum up each features, we divide it by 4. We sum up each features, we divide by 4. We find the mu for each token, and then each features minus mu, we will get deviation and square the deviation and over standard deviation of this row token, then we will have the residual. So here is the each feature minus mu over the standard deviation. Now for the start, we do it. That's how we did it. That's the deviation, and then the square of the deviation, and then the variance of the deviation divided by 4, and the square root, that's 0.2. Now, the variance here, 0.345 divided by 2, that's the deviation. That's the deviation for this one. This is the deviation for this one. And this is the deviation. and this is deviation. Each one of them divided by the variance, by the standard deviation, then we will get the results. And that's normalization for it. I think normalization is done. Let me take you to for talking to same story, for talking to the same story, and token tree I have same story. So normalization is done. Now this is final decoder self-attention. After residual, and layer normalization. So this is we are here, we've done it. So that's the output that we have that goes here, and it comes, right now we are here. So we found this output here, and now we want to get the output, the input represented by K and view from encoder. So they'll come, and you can see these two arrows. They'll go into multi-head attention. We create cross multi-head attention, and this is the Q for the decoder. This is the Q for the decoder. This is the Q. So Q from the decoder and KV from encoder. So that's what we are doing. So decoder queries, this is from the decoder, okay, that we have, that we created, that's the results earlier. 3 tokens, S, Anna, and Ahab. So S start token, and decoder, it is KV means what? KV means I like Rojava. So the sentence and translated sentence in decoder in Arabic start and ahab and this I like, they will be combined to get cross attention between encoder input representation and decoder output, which is represented by Q, and encoder represented by K and V. So here, this is the encoder that we got it from earlier class, and this is the decoder. So now we need to do attention for them. And before that, we need to create weight matrix, WK, WV, WQ. So they are saying for simplicity, 4 by 2, 4 rows by 2 columns. And then we will get Q from the output, this Q multiplied by the weight matrix. We will get Q1, Q2, and Q3. The Q is done, which is, yeah, and then we will multiply that Q. We will do the same thing for the encoder. The encoder is this, by the way, that's the encoder. We create weight matrix for encoder, and we multiply keys and values by the encoder. So that is the value of K1, K2, K3, and since we have the Q and we have the K and value, so we will get the formula of the attention, this cross attention. Q represent the output from the decoder multiplied by K, transfer the input representation from the encoder, and over dk, which is 4. Dk is 4 divided by 2, that's dk. Square root of dk, 0.7. Now we try to get this value, softmax it, and multiply by v. So we are here, we softmax it. We know how softmax right now works. we'll take each row, we sum them up, and we get the exponential of each feature. For each feature, we get the exponential for each feature, and then we will divide each exponential feature by the sum of all features exponentials. Now, for token 1 is done, for token 2 is done, for token 3 is done. So scale them and apply softmax. That's the softmax for the first row. Here is the attendance 0.34, 4.6 highest. And here the attendance is, that's the highest. And here is the attendance is the highest. Yes. This is that, sorry, not this one. So this is the highest attendance, and this is the highest attendance. Now we multiply by V, we will get V, earlier we had it, which is equals K, same value of K. Now we multiply the softmax, the result of the softmax multiplied by V. That's how we get the results. That's for the second token, and that's for the third token. Now, this is the cross attention for encoder, decoder. Encoder represented by K and V, decoder represented by Q, and that is the cross attention output. Now we understand exactly what happens in the decoder cross attention and why. We're still translating I like Rojava to Arabic. So this is more about the purpose of cross attention. Decoder wants to generate the next word in Arabic. At this point, each decoder token already knows previous target tokens. Via decoder, it's self-attention. But it also needs to look at the source encoder. So we need to know the K and V, but we have still Q from decoder. Now, these are definitions that I put them down. That's how to know the mechanism. Now, that's the final output from cross attention. Now, next, we have to do, now we've done this one, we've done this one, we've done this one, and we've done this one. Now, we have the output that goes to add a normal, and we have the output skipping goes to here. So this output, that's that output before cross attention plus the output from cross attention. So basically, I can put it in this way. Basically, this output before skipping multi-attention plus this output. That's what we are going to do. Plus this output. I put in blue. Plus this output. Okay. So then we create add. That's add. Add means what? The output in green and before cross attention plus the output from cross attention, which is in blue arrow here. That means we do residual, add residual, and then we normalize it. So that is the before cross attention, and this is cross attention. Now we have a technical problem. This is 3 by 2, and this is 3 by 4. Now what we are going to do, we make a copy of this bit here. That's the copy is done. And then we add later on. So this is the copy of the 1 minus 1.9, 1.91, and minus 1.9 copied, 1.9 copied, 1.91 copied, and the rest copied as it is. So we have two parts of C, okay, because we want to make it 3 by 4. Once 3 by 4 and this one 3 by 4, we can add this with this. So this is add with this. Now, minus 1.5 to 1.25 plus minus 1.90, 1.42 plus 1.91, so on and so forth. And that's how we did it, okay, for 3 tokens. And then we normalize it. Again, the normalization already, we know about it. We did it in coding. We did it in decoding several times because the normalization and residual normalization always repeated so that to get better values for the training to be a smooth numerical values for the training. So to speed the training, that's the main purpose. So here we take each row and we sum them up, get the mu, and take each value minus mu, subtract from mu, and get the deviation, square the deviation, and then divide it by the standard deviation. That is normalized. Okay, so the details of all this, that's the deviation. So this deviation divided by 2.834, then you get this value. 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 So these are the values that we have them. That's the first token, and the second token also done, and the third token also done. And now the weight matrix is this one. That's the weight matrix. So now we are doing, we did residual layer and cross attention, and then that's done with this so far, done with this, done with this, done with this, done with this. Now we do feed forward. For the feed forward, we would have this formula, rectified linear unit, this part, this is H1. If you multiply it by W2, this W2, so that is H2. So H1 multiply by W2 plus B2, so of course plus B2, so that is H2. That's the equation. So let's do X is the one we had it here. That's our X. Multiply by, we need to create a weight matrix 1, weight matrix 2, we need to initialize it. That's weight matrix 1, weight matrix 2, and weight matrix 4 by 4, weight matrix 4 by 4. And now we have to do a rectified linear unit multiplied by W plus B1. That is all H1 multiplied by W2 plus B2. That's H2. So here's the result of the first token. Apply ReLU. We'll take all the minus values. This minus values become 0. Minus values become 0. So, and that is the result for it. 0 point, minus value 0, minus value 0. And then the rest, it's fine. Okay. So that is the adding bias to it as well. We added bias to it. That's the after adding bias, and we do ReLU for it. Bias 1, of course. Now this one is 0. This one is 0. The rest all stays. So here the results after 0. So not here. Just apply according to the equation. So according to the equation, that is the rectified unit, rectified linear unit. It is here. Okay, so applying rectified linear unit to this, which is H1, they will be ready to go to be multiplied by W2 so that we will get hidden 2. So done for the first one, and we will do for the second token. Once you have this one, this multiply by W2 plus B2. So that's actually this H. This H1. This should be H1. So for the token 2, again, we have the same thing. That is the results. Here, preload, this one becomes 0, this one becomes 0. And that's the results for it. That is the result for it. Of course, this one multiplied by W2. Here is the, sorry, just forget about this one. Let me just explain it one more time. For those, now, if we just explain it in this way, now that's W1. After W1 is done, then we'll be reload. So this is, so just get the pen. So multiplying by W1, so means we need to apply ReLU to it. So once apply ReLU, it'll you will have this one 0, this one as it is, this one 0, and this one as it is. That's it. So this is your H1. H1 multiplied by W2 plus bias, then you have this value. Likewise, we do it for AHAB. That's the ReLU. This one's 0, this one's 0. The rest will be there, plus W2, and add bias, nothing changes there. So now we're done with the feed forward. Done. Then we come to here. Add a normalization. Here is the output of the feed forward. We do residual, adding residual to it, and we normalize, which is very basic and repeated. So here the earlier, this is the output from the feed forward, and this before going into feed forward. Before going into feed forward, I just take you back so that you can see. That is before going to the feed forward. That's the before. So minus 1.11 before going to feed forward. That is X before going to feed forward, plus the output from feed forward, element-wise 0 plus this one plus this one, 0 plus this one plus this one, so on and so forth. Now this is done. We found residual. That's the results for it. Normalize of this one. So we add up all these features for the first row. This plus this plus this plus this, divide by 4. That's mu. When divided by 4, you get mu. Then each feature minus mu, and then square it, and then get the standard deviation, and then divide the difference deviation square by the standard deviation, and then you get the normalize. Now, that is the equation of layer normalize. Each feature row-wise will be added to each other, get the mu, and once you found the mu, each feature minus mu, square it, and and square it and sum all the squares and divide them by the mean. Then you get the standard deviation, variance and standard deviation. And now divide each deviations, that's the deviation, which is square root of this one, my, xi, minus mu squared. We will get for the first row and we get for the second row, we get for the third row. Now that's done. Now this is our output after our output after the layer normalization. That's for the first token, this one for the second token, and third token. That's the final output. Next, so that's what we have. The final output, we will do now. Each token embed is now fully processed by one decoder layer, which includes self-attention previous, cross-attention, decoder encoder, and includes feed-forward, residual, and normalization. If I take it, so what happened now here, this is the output that we have found so far. Well, this output is result of add and normalization, and feed-forward, and add and normalization, cross-validation, add and normal, and self-attention. So now all this process, we got this output, and this output, we need to subject it to linear. Now, that's what we are doing right now. Let's see where we are. That's the linear. So we have start, Ana, Ahab, Rojava. These are the tokens that we have. So we will have a matrix 5 by 4, 5 by 4, but then we project it, we make it 4 by 5. So, and that's the bias. So that's how we do linear. That's the linear equation, XWO plus bias O. That's the linear equation. Now, this is the original input matrix that we have before applying linear. And what we are going to do, this row multiplied by this column, 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 and this row multiplied by this column. So we transfer the weight matrix from 5 to 4 to 4 to 5, from 5 to 4 to 4 to 5. And then the second row multiplied by this, second row multiplied by this, second row multiplied by this, second row multiplied by the column, and so on and so forth. Now, and then we add the bias vector. So that's for the first score, second score, third score, fourth score, and fifth score. So adding bias, we will have this results. For the second token, again, the operation that I've done, and adding bias to it. And the third token, likewise, we have the first score, second, adding bias. So eventually we have this output matrix. Eventually we have this output matrix. Now, that's the final output from the linear. This is the linear equation. We created weight matrix, and we multiplied the x that comes from the original x multiplied by the weight matrix, and we get this value. Next, now the output is done from here. Now, the last process is softmax. And the softmax means the purpose of softmax, finding the probability of each token. So here is the output from the linear, just from here. What we are going to do, we will take exponential of this one, exponential of this one, exponential of this one, and exponential of this one, and exponential of this one. Then we take the exponential of all of the exponential, and each feature divided by sum of all exponential. So that's what we are going to do. These are the score. This is the each feature exponential over the sum of all feature exponential. So that's the exponential for this one is this exponential, and for zero is one. See, for zero is one. Now we will get the sum of them. Once we get the sum of them, and then each one of them divided by the sum. So 0.581 divided by 5.516. 1.828 divided by 5.516. 0.643 divided by 5.516, and 1.464 divided by 5.516. 1 divided by 5.56. So all of them, uh, uh, all of them. So that's how we are going to get the result. That's the softmax. We got it. And that's for this all should equal 1. 0.105 plus 0.331 plus 0.11 should all equal 5. Okay. Now, we do for ANA as well, for ANA token as well. So that's the score. We get the exponential for each one of them. We get the exponential for each feature over the sum of all features. That's how we are getting them. And the sum should be this one. Now, so that's how we're going to work with that one. Now, then again, for the what happened, you can see the softmax. There is a value. I should see this 0.312 is the highest, which means that kind of in the training, the ANA is predicted. And let's see this one. Which one is the highest? Okay, for the softmax, we just check this one. So this one is the highest. Again, this is S, the first token S, and the second token is ANA. So it means this one also was predicted. And for the last one, the softmax value is again 0.310. That's the highest, means ANA is predicted. Why? What? Because it was a simplified illustration, and we just assumed the weights, and that's how this is just for learning. But actual transformer decoder should have different values, realistic values, and what we did so far is just simplicity, just for learning. And you can see the possibilities all came in the ANA, in the bold. And I gave the reason. But in real life, you don't have this type of things. So that's more or less about the transformer decoder explanation. And if you have anything, the links are there. And if you have any question, you can just drop me an email, and I'll be happy to answer you. So stay tuned for the next tutorials. Thank you very much.